Hello everyone. The topic that we are going to discuss today is the P block elements. We have already completed group 13 and group 14 elements of the periodic table of class 11th. The topic that we are going to continue today would be group 15 and so on of your class 12th. And I would like to thank you all for your lovely comments and suggestions. I'm really impressed. It feels like though we haven't seen each other, but there's some connection uh, between us. So it really feels great. Thank you for being there, and I really appreciate it. So, without wasting any time, let's get started. The P block elements. Diversity in chemistry is the hallmark of P block elements, manifested in the ability to react with the elements of S, D, and F blocks as well as with their own. In class 11th, you have learnt that the p block elements are placed in group 13 to 18 of the periodic table. Their valence shell electronic configuration is ns2 np 1 से 6 तक, except helium which has 1s2 configuration. The properties of p block elements, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of d orbitals in second period and presence of d or DNF orbital in heavier elements starting from third period onwards have significant effects on the properties of elements. In addition, the presence of all the three types of elements, metal, metalloids, and nonmetals, bring diversification in chemistry of these elements. Having learnt that the chemistry of elements of group 13 and 14 of P block of periodic table in class 11, you will learn the chemistry of elements of subsequent groups in this unit. Group 15 elements. Group 15 includes nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are nonmetals, arsenic and antimony metalloids, bismuth and moscovium are typical metals. Molecular nitrogen comprises 78% by volume of the atmosphere. In the Earth's crust, it occurs as sodium nitrate, NaNO3, called Chile saltpeter, and potassium nitrate, Indian saltpeter. It is found in the form of proteins in plants and animals. Phosphorus occurs in minerals of the apatite family. Calcium 9 in bracket PO4 6 times. Calcium X2 where X is equal to fluorine, chlorine or OH. Example, fluorapatite, calcium 9, PO4 6 times dot CaF2, which are the main components of phosphate rock. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. Moscovium is a synthetic radioactive element. Its symbol is Mc. Atomic number 115, atomic mass 289, and electronic configuration Rn 5f14 6d10 7s2 7p3. Due to very short half-life and availability in very little amount, its chemistry is yet to be established. Here, except for moscovium, important atomic and physical properties of other elements of this group along with their electronic configuration are given in table 7.1. So you all know what are the elements: nitrogenous, phosphorus, arsenic, antimony and bismuth. So the mnemonic would be for nitrogen, Na पैसा, असली, सब भिखारी. Okay, so nitrogen, na, paisa, asli, sab bhikhari is the mnemonic for group 15 elements. Trends of some of the atomic, physical, and chemical properties of group are discussed below. Electronic configuration. The valence shell electronic configuration of these elements is ns2 np3. The s orbital in these elements is completely filled and p orbitals are half filled, making the electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic in a particular state radii increase in size down the group. There is a considerable increase in covalent radius from nitrogen to phosphorus. However, from arsenic to bismuth, only a small increase in covalent radius is observed. This is due to the presence of completely filled d and or f orbitals in heavier members. Ionization enthalpy. Ionization enthalpy decreases down the group due to gradual increase in atomic size. Because of the extra stable half-filled p orbitals, electronic configuration and smaller size, the ionization enthalpy of the group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of successive ionization enthalpy as expected is, that is, the third ionization will be very higher than the second one and then the first. Electronegativity. The electronegativity value in general decreases down the group with increasing atomic size. However, amongst the heavier elements, the difference is not that much pronounced. Physical properties. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas while all other are solids. Metallic character increases down the group. Nitrogen and phosphorus are nonmetals. Arsenic and antimony metalloids, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. The boiling points in general increase from top to bottom in the group, but the melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all the elements show allotropy. Chemical properties, oxidation states, and trends in chemical reactivity. The common oxidation states of these elements are -3, +3, and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. In fact, last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. The only well characterized bismuth 5 compound is BiF5. The stability of +5 oxidation state decreases and that of +3 state increases due to inert pair effect down the group. Besides +5 oxidation state, nitrogen exhibits +1, +2, +4 oxidation state also when it reacts with oxygen. However, it does not form compounds in +5 oxidation state with halogens as nitrogen does not have d orbitals to accommodate electrons from other elements to form bonds. Phosphorus also shows +1 and +4 oxidation states in some oxo acids. In case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. For example, 3HNO2 will give HNO3 plus water plus NO, 2NO. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into plus 5 and minus 3 both in alkali and acid. However, plus 3 oxidation state in case of arsenic, antimony, and bismuth becomes increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4 since only 4 1s and 3p orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell, which can be used for bonding or covalency and hence expand their covalency, as in pF6 minus. Anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its small size, high electronegativity, high ionization enthalpy, and non availability of d orbitals. Nitrogen has unique ability to form p pi multiple bonds with itself and with other elements having small size and high electronegativity. Example, carbon, oxygen. Heavier elements of this group do not form p pi bonds as their atomic orbital are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exists as a diatomic molecule with a triple bond, 1s and 2p between the two atoms. Consequently, its bond enthalpy, 941.4 kJ per mole, is very high. On the contrary, phosphorus, arsenic, and antimony form single bonds as phosphorus, arsenic, and antimony, while bismuth forms metallic bonds in elemental state. However, the single nitrogen bond is weaker than the single PP, that is phosphorus bond, because of high interelectronic repulsion of the non bonding electrons owing to the small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d p pi bond as the heavier elements can. Example, R3p bonded to oxygen, doubly bonded, or R3p double bond CH2, where R is the alkyl group. Phosphorus and arsenic can form d pi bond. Also with transition metals when their compounds like phosphorus in bracket ethyl, that is C2H5 thrice, and arsenic C6H5 3 act as ligands. Reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E can be nitrogen, phosphorus, arsenic, antimony, or bismuth. Some of the properties of these hydrides are shown in the table 7.2. The hydrides show regular gradation in their properties. The stability of hydrides decreases from ammonia to BiH3, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increases. Ammonia is only a mild reducing agent, while BiH3 is the strongest reducing agent among all the hydrides. Basicity also decreases in the order, NH3 being the greatest, then PH3, then ASH3, then SBH3, which is almost nearly equal to BiH3. Due to high electronegativity and small size of nitrogen, NH3 exhibits hydrogen bonding in solid as well as liquid state. Because of this, it has higher melting and boiling point than that of PH3. So you can look at the table below where there is a comparison given between the melting point and boiling point, also between the bond length of the group 15 elements and hydrogen. Reactivity towards oxygen. All these elements form two types of oxide. E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That of arsenic and antimony, amphoteric, and those of bismuth predominantly basic. Reactivity towards halogens. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide. The reason you all know, because there is no availability of d orbital in its valence shell. Pentahalides are more covalent than trihalides. This is due to the fact that in pentahalides plus 5 oxidation state exist, while in the case of trihalides plus 3 oxidation states exist. Since elements in plus 5 oxidation state will have more polarizing power than in plus 3 oxidation state, the covalent character of bond is more in pentahalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except BIF3 are predominantly covalent in nature. Reactivity towards metal. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2, that is calcium nitride, Ca3P2, calcium phosphide, Na3As, sodium arsenide, Zn thrice Sb2, zinc antimonide, and Mg3Bi2, magnesium bismuthide. Example: though nitrogen exhibits plus 5 oxidation state, it does not form pentahalide. What is the reason? Nitrogen with N is equal to 2 has s and p orbitals only. It does not have d orbital to expand its covalency beyond 4. That is why it does not form pentahalide. pH3 has lower boiling point than NH3. Why? Unlike NH3, pH3 molecules are not associated through hydrogen bonding in liquid state. That is why the boiling point of pH3 is lower than that of NH3. Dinitrogen. Preparation. Dinitrogen is produced commercially by liquefaction and fractional distillation of air. Liquid dinitrogen, boiling point 77.2 Kelvin, distills out first, leaving behind liquid oxygen. In laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. NH4Cl aqueous plus NaNO2 aqueous will give N2 plus 2H2O plus NaCl. Small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by thermal decomposition of ammonium dichromate. NH4 the whole twice, Cr2O7, heat N2 plus 4H2O plus Cr2O3, that is chromium oxide. Very pure nitrogen can be obtained by thermal decomposition of sodium or barium azide. Ba in bracket N3, close the bracket twice, it will give you barium separated and 3 nitrogen gas evolved. Properties. Dinitrogen is a colorless, odorless, tasteless, and non-toxic gas. Nitrogen atom has two stable isotopes, N14 and N15. It has a very low solubility in water, 23.2 cm cube per liter of water at 273 Kelvin and 1 bar pressure, and low freezing and boiling points. तो क्या है, लो solubility भी है, लो freezing point भी है and लो boiling points भी है. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of nitrogen-nitrogen triple bond. Reactivity, however, increases rapidly with rise in temperature. At higher temperatures, it directly combines with some metals to form predominantly ionic nitrides and with non-metals covalent nitrides. A few typical reactions are 6Li plus N2 in, in the presence of heat will give you lithium nitride, Li3N. Magnesium with nitrogen, it will give Mg3N2. It combines with hydrogen at about 773 Kelvin in the presence of a catalyst known as Haber's process to form ammonia. So dinitrogen reacts with hydrogen at 773 Kelvin to give ammonia. Dinitrogen combines with dioxygen only at very high temperature, that is at about 2000 Kelvin to form nitric oxide, NO. Uses. The main use of dinitrogen is in the manufacture of ammonia and other industrial chemicals containing nitrogen. Example, calcium cyanamide. It also finds use where an inert atmosphere is required. Example, in iron and steel industry. Inert diluent for reactive chemicals. Liquid dinitrogen is used as a refrigerant to preserve biological materials, food items, and in cryosurgery. Write the reaction of thermal decomposition of sodium azide. Thermal decomposition of sodium azides give dinitrogen gas. NaNA3, Na that is sodium, N3 that is nitrogen. Azide, N3. 2Na plus 3N2. It will give dinitrogen gas. Ammonia. Preparation. Ammonia is present in small quantities in air and soil where it is formed by the decay of nitrogenous organic matter. Example, urea. NH2 C double bond O NH2, that is urea, reacts with water to give nitrogenous organic matter and it gives ammonia in release, that is water plus carbon dioxide. On a small scale, ammonia is obtained from ammonium salts which decompose when treated with caustic soda or calcium hydroxide. So you can go through the reaction. The key point is what? Ammonia is obtained from ammonium salts. कब? ये small scale पे होगा. When which decomposes when treated with caustic soda or calcium hydroxide. On a large scale, ammonia is manufactured by Haber's process. N2 plus 3H2 will give you ammonia. In accordance with Le-Chatelier's principle, high pressure would favor the formation of ammonia. The optimum conditions for the production of ammonia are a pressure of 200 into 10 raised to 5 Pascal, about 200 atmosphere, a temperature of 700 Kelvin, and the use of catalysts such as iron oxide with the small amounts of K2O and Al2O3 to increase the rate of attainment of equilibrium. The flow chart for the production of ammonia is shown in figure 7.1. Earlier, iron was used as a catalyst with molybdenum as a promoter. Properties. Ammonia is a colorless gas with a pungent odor. Its freezing point and boiling points are 198.4 and 239.7 Kelvin respectively. In the solid and liquid state, it is associated through hydrogen bonds as in case of water, and that accounts for its higher melting and boiling points than expected on the basis of its molecular mass. The ammonia molecule is trigonal pyramidal with the nitrogen atom at the apex. It has 3 bond pairs and 1 lone pair of electron as shown in the structure. Ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to the formation of OH- ions. Ammonia gas reacts with water. It gives ammonium ion plus hydroxyl, that is OH minus ion. It forms ammonium salts with acids, example ammonium chloride, ammonium sulfate, etc. As a weak base, it precipitates the hydroxides, hydrated oxide in case of some metals, of many metals from their salt solution. For example, you can go through the zinc sulfate and ferric chloride. When it reacts with ammonium hydroxide, what is that you get? You can look at the reaction as shown in the screen, on the screen. Okay. The presence of a lone pair of electrons on the nitrogen atom of the ammonia molecule makes it a Lewis base. It donates the electron pair and forms linkage with metal ions, and the formation of such complex compounds find application in detection of metal ions such as copper 2 plus, Ag plus. Copper 2 plus reacts with ammonia to form a complex compound which is deep blue in color. The complex would be CuNH3,4 tetrahedral complex with cationic, which is a cationic complex. Again, silver Ag plus reacts with Cl minus to give silver chloride, the white precipitate. AgCl reacts with ammonia to give complex compound AgNH3 twice and Cl in the outer sphere. Uses: ammonia is used to produce various nitrogenous fertilizers. Ammonium nitrate, urea, ammonium phosphate, and ammonium sulfate, and in manufacture of some inorganic nitrogen compounds. The most important one being nitric acid. Liquid ammonia is also used as a refrigerant. Example: why does ammonia act as a Lewis base? Nitrogen atom in ammonia has one lone pair of electrons which is available for donation. Therefore, it acts as a Lewis base. Oxides of nitrogen. Nitrogen forms a number of oxides in different oxidation states. The names, formulas, preparation, and physical appearance of these oxides are given in the table 7.3. So here you can look at the table oxides of nitrogen. There are dinitrogen oxide. Dinitrogen oxide को हम N2O कहते हैं. Nitrogen monoxide NO. Dinitrogen trioxide N2O3. Nitrogen dioxide NO2. Dinitrogen tetroxide तो N2O4. Dinitrogen pentoxide N2O5. It is very important that you should know what are the physical appearance or what are the characteristic of these oxides. Okay, the questions can be asked. Lewis dot main resonance structure and bond parameters of oxides are given in the table 7.4. देखो यहाँ पर N2O एंड उसके रेजोनेंस स्ट्रक्चर्स भी दिए हुए हैं. सो इट इज़ वेरी इंपॉर्टेंट दैट यू शुड नो कि कहाँ पर डबल बॉन्ड है, कैसे मतलब ये स्ट्रक्चर कैसे एग्जिबिट होता है. क्वेश्चंस इस पर भी आ चुके हैं, तो यू हैव टू बी वेरी अलर्ट वाइल गोइंग थ्रू दिस. यू शुड नो ऑल द ऑक्साइड्स ऑफ नाइट्रोजन एंड उसके स्ट्रक्चर तो पता होना ही चाहिए. ओके. Why does NO2 dimerize? NO2 contains odd number of valence electron. It behaves as a typical odd molecule. On dimerization, it is converted to stable N2O4 molecule with even number of electrons, and thus it will dimerize. Nitric acid. Nitrogen forms oxo acids such as H2N2O2, hyponitrous acid, H2N2O2, hyponitrous acid. तो nitrous acid क्या है? HNO2. ठीक है, and HNO3 nitric acid. Amongst them, HNO3 is the most important. Preparation. In laboratory, nitric acid यानी HNO3 is prepared by heating KNO3 or NaNO3 and concentrated H2SO4 in a glass retort. NaNO3 plus H2SO4 gives NaHSO4 plus HNO3. On a large scale, it is prepared mainly by Ostwald's process. This method is based upon catalytic oxidation of NH3 by atmospheric oxygen. तो स्टूडेंट्स क्वेश्चन क्या आ सकता है, अभी देखो यहाँ पर लिखा हुआ है ऑन अ लार्ज स्केल इट इज प्रिपेयर्ड मेनली बाय ओसवाल्ड प्रोसेस. तो क्वेश्चन कैन बी नाइट्रिक एसिड ऑन अ लार्ज स्केल इज प्रिपेयर्ड बाय डैश प्रोसेस, और आपको 4 ऑप्शन दे देंगे, हेबर्स प्रोसेस, ओसवाल्ड प्रोसेस, XYZ फलाना ढिमकाना प्रोसेस. तो ये छोटी छोटी चीज़ें हैं बट इम्पॉर्टेंट हो जाती है. ओके, ऐसा मेरी टीचर ने मुझे बताया था. ओके, so 4NH3 plus 5O2, it will in the presence of platinum or RH gauge catalyst at 500 Kelvin and 9 bar pressure, it will give 4NO plus 6H2O. Nitric oxide thus formed combines with oxygen giving NO2. तो जो NO नाइट्रिक ऑक्साइड बना है वो क्या करेगा, ऑक्सीजन से कंबाइन कर लेगा और NO2 दे देगा. अब नाइट्रोजन डाइऑक्साइड सो फॉर्म डिजोल्व इन वाटर टू गिव नाइट्रिक एसिड. ठीक है, तो ये लंबा प्रोसेस है. पहले अमोनिया से नाइट्रिक ऑक्साइड बना, नाइट्रिक ऑक्साइड कन्वर्ट हुआ एंड नाइट्रोजन डाइऑक्साइड बना, एंड वो नाइट्रोजन डाइऑक्साइड पानी में घुल के क्या बन गया, नाइट्रिक एसिड. NO thus formed is recycled and the aqueous HNO3 can be concentrated by distillation up to 68% by mass. Further concentration to 98% can be achieved by dehydration with concentrated H2SO4. Properties: it is a colorless liquid, freezing point 231.4 Kelvin and boiling point 355.6 Kelvin. Laboratory grade nitric acid contains approximately 68% of nitric acid by mass and has a specific gravity of 1.504. In gaseous state, HNO3 exists as a planar molecule with the structure as shown. In aqueous solution, nitric acid behaves as a strong acid giving hydronium and nitrate ions. HNO3 reacts with water to give hydronium H3O positive and NO3 minus ions. Concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The products of oxidation depend upon the concentration of the acid, temperature, and the nature of the material undergoing oxidation. 3 copper plus 8 HNO3 in dilute state, it will give you copper NO3 twice plus 2NO plus 4H2O. ठीक है, copper again reacts with nitric acid, it forms copper nitrate plus nitrogen dioxide plus water. Zinc reacts with dilute nitric acid to give N2O and with concentrated acid to give NO2. तो यहाँ पर देखो दो चीज बहुत इंपॉर्टेंट है. जिंक जब डाइल्यूट नाइट्रिक एसिड से रिएक्ट कर रहा है तो वो क्या दे रहा है, N2O डाई नाइट्रोजन ऑक्साइड. लेकिन जब जिंक कॉन्सेंट्रेटेड नाइट्रिक एसिड से रिएक्ट कर रहा है तो वो क्या दे रहा है, नाइट्रोजन डाइऑक्साइड. अगेन एन इंपॉर्टेंट क्वेश्चन. Some metals, example chromium, aluminium, do not dissolve in concentrated nitric acid because of the formation of a passive film of oxide on the surface. Concentrated nitric acid also oxidizes non-metals and their compounds. Iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid, and phosphor to phosphoric acid. Brown ring test. The familiar brown ring test for nitrates depend on the ability of Fe2 plus to reduce nitrates to nitric oxide, which reacts with Fe2 plus to form a brown colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion and then carefully adding concentrated sulfuric acid along the sides of the test tube, a brown ring at the interface between the solution and sulfuric acid layers indicating the presence of nitrate ion in the solution. सो दिस बिकम्स वेरी इंपॉर्टेंट ब्राउन रिंग टेस्ट. और आपको ये भी पूछते हैं, कोऑर्डिनेशन केमिस्ट्री का बहुत इंपॉर्टेंट क्वेश्चन बन जाता है. पूछते हैं कि जो कॉम्प्लेक्स बना है ब्राउन रिंग टेस्ट में उसका नाम क्या है, या फिर उसको वो कॉम्प्लेक्स कैसे दिखता है. तो यहाँ पर आप देख रहे हो क्या है, Fe इज द सेंट्रल मेटल आयन, H2O 5 टाइम्स एंड NO. उसके बाद में द होल इट इज अ कटायनिक कॉम्प्लेक्स विथ 2+ चार्ज ऑन इट. तो ये है कॉम्प्लेक्स जो बनता है जब ब्राउन रिंग टेस्ट कंप्लीट होती है. So the question becomes important, and brown ring test itself is an important aspect. Okay, uses. The major use of nitric acid is in the manufacture of ammonium nitrate for fertilizers and other nitrates for use in explosive and pyrotechnics. It is also used for preparation of nitroglycerin, trinitrotoluene, and other organic nitro compounds. Other major uses are in pickling of stainless steel, etching of metals, and as an oxidizers in rocket fuels. Phosphorus. Phosphorus is found in many allotropic forms, the most important ones being white, red, and black. White phosphorus is a translucent with white waxy solid. It is poisonous, insoluble in water, but soluble in carbon disulfide and glows in dark chemiluminescence. It dissolves in boiling NaOH solution in an inert atmosphere, giving pH 3. Phosphorus P4 plus 3 NaOH, sodium hydroxide, and water, it will give pH 3 plus sodium hypophosphite, sodium Na, H2PO2, hypophosphite. White phosphorus is less stable and therefore more reactive than the other solid phases under normal condition because of angular strain in the P4 molecule, where the angles are only 60 degree. It readily catches fire in air to give dense white fumes of P4O10. P4 reacts with 5 oxygen molecules to give P4O10. It consists of discrete tetrahedral P4 molecule as shown in figure 7.2. So P4 patang-like structure. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin in an inert atmosphere for several days. सिंपल है ना. रेड फॉस्फोरस कैसे बनेगा, पहले व्हाइट था, आपने उसको हीट कर दिया, जला दिया, तो क्या हो गया, रेड फॉस्फोरस बन गया. एंड द टेम्परेचर इज 573 Kelvin. When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed. Red phosphorus possesses iron grey luster. It is odorless, non-poisonous, and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. It is polymeric, consisting of chains of P4 tetrahedral linked together in the manner as shown in figure 7.3. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 Kelvin. It can be sublimed in air and has opaque, monoclinic or rhombohedral crystals. It does not oxidize in air. Beta black phosphorus is prepared by heating white phosphorus at 473 Kelvin under high pressure. It does not burn in air up to 673 Kelvin. Phosphine. Preparation. Phosphine is prepared by the reaction of calcium phosphide with water or dilute HCl. Ca3P2, calcium phosphide, plus water will give calcium hydroxide plus 2 phosphine. Calcium phosphide reacts with HCl to give calcium chloride plus phosphine. In laboratory, it is prepared by heating white phosphorus with concentrated NaOH solution in an inert atmosphere of carbon dioxide. P4 plus 3 NaOH plus 3 water gives phosphine plus 3 NaH2PO2. NaH2PO2. H2PO2 को क्या बोला था हमने? Hypophosphite. Sodium hypophosphite NaH2PO2. When pure, it is non-inflammable but becomes inflammable owing to the presence of P2H4 or P4 vapors. To purify it from the impurities, it is absorbed in HI to form phosphonium iodide PH4I, which on treating with KOH gives off phosphine, that is PH3. Properties: it is a colorless gas with rotten fish smell and is highly poisonous. It explodes in contact with traces of oxidizing agents like HNO3, Cl2, and Br2 vapors. It is slightly soluble in water. The solution of pH3 in water decomposes in presence of light, giving red phosphorus and H2 when absorbed in copper sulfate or mercuric chloride solution. The corresponding phosphides are obtained. Copper sulfate reacts with phosphine to give Cu3P2 plus H2SO4, that is copper phosphide. HgCl2 reacts with phosphine to give Hg3P2 plus 6HCl. Phosphine is weakly basic and, like ammonia, gives phosphonium compounds with acids. Example PH3 plus HBr, it gives PH4Br. Uses: the spontaneous combustion of phosphine is technically used in Holmes signal. Containers containing calcium carbide and calcium phosphide are pierced and thrown in the sea when the gases evolved, burn, and serve as a signal. It is also used in smoke screens. Example 7.6. In what way can it be proved that pH3 is basic in nature? Phosphine reacts with acid like HI to form PH4I, which shows that it is basic in nature. PH3 plus HI, it becomes PH4I. Due to lone pair on phosphorus atom, PH3 is acting as a Lewis base in the above reaction. Phosphorus halides. Phosphorus forms two types of halides, PX3 and PX5. एक्स तो आप लोग को पता ही है क्या होता है, फ्लोरीन, क्लोरीन, ब्रोमीन, आयोडीन. हाँ, X5 तो PI5 कभी नहीं बनेगा. Preparation of phosphorus trichloride. It is obtained by passing dry chlorine over heated white phosphorus. P4 plus 6Cl2 will give 4PCl3, that is phosphorus trichloride. It is also obtained by action of thionyl chloride with white phosphorus. P4,8SOCl2 will give 4PCl3, 4SO2 plus 2S2Cl2. Properties: it is colorless, oily liquid and hydrolyzes in the presence of moisture. PCl3 plus water gives H3PO3 plus 3HCl. It reacts with organic compounds containing OH groups such as CH3COOH, C2H5OH. You can look at the equation, a reaction that is given on the screen. It has a pyramidal shape as shown in which phosphorus is sp3 hybridized. Preparation: phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dry chlorine. P4 plus excess, matlab 10 chlorine atoms, 10 Cl2 will give 4 PCl5. It can also be prepared by the action of SO2Cl2 on phosphorus. P4 plus 10 molecules of SO2Cl2 will give 4 molecules of PCl5 and 10 molecules of SO2 gas will be released. Properties: PCl5 is a yellowish white powder and in moist air it hydrolyzes to POCl3 and finally gets converted to phosphoric acid. PCl5 plus H2O, POCl3 plus 2HCl. POCl3 plus 3H2O will give H3PO4 plus 3HCl. When heated, it sublimes but decomposes on stronger heating. PCl5 को heat करोगे तो क्या मिल जाएगा? PCl3 plus chlorine will get released. It reacts with organic compounds containing OH group, converting them to chloroderivatives. C2H5OH reacts with PCl5 to give ethyl chloride plus POCl3 plus HCl. तो reaction आप देख लो screen पे. Me reading would be not that effective, though you seeing at the screen. Finally, finely divided metals on heating with PCl5 gives corresponding chlorides. 2Ag plus PCl5 corresponding chloride तो silver chloride मिल जाएगा. Sn plus 2PCl5 तो क्या मिल जाएगा? SnCl4 plus 2PCl3. It is used in the synthesis of some organic compounds, example ethyl chloride, then CH3C double bond OCl, acetyl chloride. In gaseous and liquid phases, it has a trigonal bipyramidal structure as shown. The three equatorial PCl bonds are equivalent, while the two axial bonds are longer than the equatorial bonds. This is due to the fact that the axial bond pairs suffer more repulsion as compared to the equatorial bond pairs. Example 7.7. Why does PCl3 fume in moisture? PCl3 hydrolyzes in the presence of moisture, giving fumes of HCl. PCl3 plus 3H2O will give H3PO3 plus 3HCl. Example 7.8. Are all the 5 bonds in PCl5 molecule equivalent? Justify your answer. अभी हमने पढ़ा the answer is obviously no. जो पांचों बॉन्ड है वो सेम नहीं है. PCl5 has a trigonal bipyramidal structure and the three equatorial PCl bonds are equivalent while the two axial bonds are different and longer than the equatorial bonds. Oxoacids of phosphorus. Phosphorus forms a number of oxoacids. The important oxoacids of phosphorus with their formulas, methods of preparation and presence of some characteristics bond in their structures are given in table 7.5. तो वापस से oxoacids of phosphorus, hypophosphorus H3PO2, इसको हम बोलते हैं phosphonic, ठीक है, phosphinic. Orthophosphorus H3PO3 phosphonic. Pyrophosphorus H4P2O5. Hypophosphoric H4P2O6. Orthophosphoric H3PO4. Pyrophosphoric H4P2O7. Metaphosphoric HPO3 in bracket N. ठीक है, तो ये नाम और उनके स्ट्रक्चर्स एंड द मॉलिकुलर फॉर्मूला बिकम्स वेरी इंपॉर्टेंट. तो see to it that you are well prepared with the names and the molecular formula. The composition of oxoacids are interrelated in terms of loss or gain of water molecule or oxygen atom. The structures of some important oxoacids are given next. In oxoacid, phosphorus is tetrahedrally surrounded by other atoms. All these acids contain at least one phosphorus and oxygen का double bond and one POH bond. The oxoacid in which phosphorus has lower oxidation state less than +5 contain, in addition to P double bond O and POH bonds, either PP, example in H4P2O6, or PH, example in H3PO2. So here it is simply trying to tell you that P double bond O and P bonded with OH, ये तो आपको मिल जाएगा देखने को. ऑल्सो जिसमें फॉस्फोरस का ऑक्सीडेशन स्टेट लेस देन +5 है, उसमें आपको P डबल बॉन्ड O एंड POH बॉन्ड्स के साथ साथ आपको P बॉन्डेड विथ P, मतलब फॉस्फोरस का बॉन्ड भी देखने मिलेगा एंड फॉस्फोरस एंड हाइड्रोजन का बॉन्ड भी देखने मिलेगा. ठीक है, बट नॉट बॉन्ड्स साथ में. ठीक है. These acids in +3 oxidation state of phosphorus tend to disproportionate to a higher and lower oxidation state. For example, orthophosphorus acid or phosphorus acid on heating disproportionates to give orthophosphoric acid or phosphoric acid and phosphine. Simple. फॉस्फोरस एसिड को अगर आपने हीट किया तो वो बन जाएगा फॉस्फोरिक एसिड. अगर मैं दूसरा नाम बोलूं, ऑर्थोफॉस्फोरस एसिड को अगर आपने हीट किया तो वो बन जाएगा ऑर्थोफॉस्फोरिक एसिड and it will also release phosphine. See students, here the structure is given. You can look at the structures of this phosphoric acid. Some even there are question asked in NEET इन प्रीवियस पेपर. तो आप लोग प्लीज़ इसके ये पी ब्लॉक में ये क्वेश्चंस बहुत बन सकते हैं एंड कुछ भी क्वेश्चंस बन सकते हैं. तो ये स्ट्रक्चर वगैरह है थोड़े इंपॉर्टेंट है, तो आप लोग फॉर श्योर देख के जाना. ओके. द एसिड्स विच कंटेन पी एच बॉन्ड, फॉस्फोरस एंड हाइड्रोजन का बॉन्ड होगा तो दे हैव स्ट्रॉन्ग रिड्यूसिंग प्रॉपर्टीज. थर्स हाइपोफॉस्फोरस एसिड इज अ गुड रिड्यूसिंग एजेंट as it contains 2 pH bond and reduces. For example, AgNO3 to metallic silver. These pH bonds are not ionizable to give H plus and do not play any role in basicity. Only those hydrogen atoms which are attached with oxygen in P bonded with OH form are ionizable and cause the basicity. Thus, H3PO3 and H3PO4 are dibasic and tribasic respectively, as the structure of H3PO3 has 2 POH bonds and H3PO4 3. Example 7.9. How do you account for the reducing behavior of H3PO2 on the basis of its structure? तो स्ट्रक्चर में देखो, इन H3PO2 two hydrogen atoms are directly bonded to phosphorus atom, which imparts reducing character to the acid. So here we complete the group 15 elements. In the next video, you will be getting group 16, group 17 and group 18 elements. Group 15 elements become very important, so see to it that you all complete it wisely. Also, I am putting down a question to you all. What do you understand by basicity? Basicity मतलब क्या? तो comment section में जाके मुझे आंसर बताइए. And if you like the video, so hit the like button, subscribe to the channel, and thank you so much for watching. Keep studying. Bye bye.